Okay, second special case of a slightly more realistic DHSS model with technological, what do you call it? Growth, anyway. Improvement in technology. Technological progress is the word I was looking for. With technological progress and capital and depreciation. Okay, in the previous one, we just had a fixed resource flow, which was called land. In this one, we're going to say, no, we've got a very large resource stock. It's so large that we don't ever need to think about the fact that it might run out. But instead of being free, it's now costly to extract. So we have to put effort into getting it out of the ground, which seems very reasonable, doesn't it? Okay, so here's the households, here's the firms, here's the labor, here's Y, here's capital investment, but we also have, here's consumption, we also have some of our product we send down the mines. Okay, I'm just going to draw the mine as a black box. Okay, but as you can see on the picture, it's like a coal mine. And the more stuff we send here instead of to the capital stock or to consumption, the more R, the bigger the flow of R. R is phi times X. Okie doke. And of course, this is still investment is S times Y minus X. So we're going to assume that we save a proportion of what's left after allowing for X, and C is 1 minus S, Y minus X. Okay, so what happens? Again, we're going to ignore the transition path and focus on balanced growth. And we know that K dot is S times Y minus X minus delta K. So K dot over K is S Y over K minus X over K minus delta. Now we need this thing, K dot over K has to be constant, so delta is constant, S is constant, we need this thing to be constant. You might argue, well, you know, Y over K could be going down and X over K could be going down as well, and that might, the two might cancel each other out. But you can, if you think carefully through it, I'm not going to take you through it, but if you think carefully through it, you can see that in the end, that is not going to work. Okay. The only way for this whole thing to be constant in the long run is if both of these are constant. So we end up with Y dot over Y equals K dot over K equals X dot over X. Which makes total sense, right? If Y doubles, investment will double, the use of the intermediate input into the energy sector or extraction sector will double, consumption will double, everything doubles. It's balanced here. Okay, so we've got that result required for balanced growth, but we still haven't solved for these, have we? To solve, we need to go again to the Cobb-Douglas, and we say that but Y dot over Y is 1 minus alpha minus beta times G, or AL dot over AL, which is just G, plus 1 minus alpha minus beta L dot over L, which is just set to 0, we could add that as well, okay? It just makes things a bit messier. Plus alpha k dot over k, which is the same as y dot over y, plus beta r dot over r. Okie doke. So 1 minus alpha y dot over y is 1 minus alpha minus beta g plus beta r dot over r. Okay, so far so good. But what are we going to do about r dot over r? Maybe if like how this is going to change is gonna no right, yeah. What are we going to do about r dot over r? I was thinking about doing something I don't need to do. The answer is here, isn't it? R is phi times x. Phi is just a constant, so r dot over r is x dot over x. X dot over x is k dot over k is y dot over y. So we can just say 1 minus alpha minus beta. This isn't a matrix, it's just a term. 1 minus alpha minus beta y dot over y is 1 minus alpha minus beta g. Y dot over y is g. Oh, so the fact that we need this resource doesn't slow growth. That's interesting. Why is that? It's because when land was fixed, that was a drag on growth because it couldn't grow. But here, R, the flow of the resource, is going to grow at the overall growth rate. So it's not a drag on growth. And, hey presto, remember those graphs we drew with GDP and resource use on a log scale, showing them tracking each other, equal growth rates. Okay, the model does the job of explaining why, or it matches the empirical observation anyway, that resource use tracks GDP. Another empirical observation that it matches is about the resource price, because the resource price here is just constant. It's actually 1 over phi. The price of x is just 1. Oops. Okay, because x and c is the same thing. It's like the final good used for something else. The final good's price normalized to 1. For every unit of x we get phi units of r. So phi is 100, then for 1 unit of x we get 100 units of r. The cost of r is 1 over 100. Okay, so WR equals 1 over phi. Constant. And that is also something we see in the data, that resource prices in the long run tend to be rather constant. In the short run, as I'm sure you're aware, they fluctuate a lot. But there's no clear long run trend when we look at 50, 100 year data series. So that is super nice. We've got a model that seems to be able maybe to explain what's going on with regard to non-renewable resources. By the way, we could have just, instead of using the final good to extract the stuff, we could have used labor and capital. The same, everything would have turned out the same. Okay. It's just, yeah. Okay, let me just check if, right, no, that's the end of this video.